The experiment for this week deals with the application of Newton's second law, which most textbooks usually give in the form you see here, that the net force experienced by an object is equal to the mass of that object multiplied by the net acceleration of the object. This week, though, what we're going to do is we're going to take this equation and we're actually going to look at it from a different perspective. So I'm just going to take this equation and rearrange it in the following format, that the net acceleration of an object, we're going to look at that as the ratio of the net force experienced by that object divided by the mass of the object. Now, this experiment is going to deal heavily with deriving an expression for the net acceleration of an object, but we're actually going to use that to try to accomplish our primary objective, which is to determine the total time of travel for an air cart that experiences both accelerated motion and motion with constant velocity. So here we have our experimental setup. It consists of two masses, mass 1 and mass 2. Mass 1 is the air cart, and the air cart will be placed on the air track, and this is before the air is forced through the air track. Mass 2 will be connected to a thin, light string that will be wrapped around mass 1, placed over a pulley, and connected to mass 2. Now, before we do anything, let's take a look at some of the forces that are at play here. For example, on mass 1, there is the force due to gravity, which acts downward. There's the normal force, which supports it in the opposite direction of the force due to gravity. And those two forces should cancel each other out, providing a net force of 0. There's also a tension force that is in the string, which attempts to pull mass 1 to the right. And without any air in the track, there is also a frictional force that acts in the opposite direction of that tension force. So as far as M1 is concerned, all the forces that are acting on it initially cancel out to 0. Now, as far as M2 is concerned, there are really only two forces that are acting on it before we turn on the air. That is the force due to gravity in the downward direction and the tension force, which is acting in the upward direction. Now, again, before air is forced through the track, the forces that are acting on M2 are also in equilibrium with each other, and as a result, there's no net force acting on M2 either. Now, initially, mass M2 is going to be positioned in such a way that it is a height above the ground, and we'll call this height delta Y. Now, when we finally do allow air to flow through the air track, we know what's going to happen here. Immediately, there will no longer be a frictional force acting on M1 to oppose the tension in the string, and as a result, the tension in the string, which is caused by mass 2 being attached to it, is going to cause the objects to begin to accelerate. And as a result, mass 2 goes down, and pulling with it mass 1 until mass 2 ends up on the ground. Now, when mass 1 starts to move, it's going to trip this photo gate, and that's going to start the timer. And you should realize the distance that M1 has traveled, what we will call delta x1, is equivalent to the height that we had measured previously for mass 2 relative to the ground, in this case delta y. Now, it's important to realize that the entire time that mass 1 was connected to mass 2, it was accelerating, which means it was changing its velocity over the entirety of the length for delta x1. But once mass 2 hits the ground, mass 1 will now be moving at a constant speed for the second portion of its trip, which we will label delta x2. At this point, the second photo gate will be tripped, and that will conclude the timing of the motion for mass 1. But it's important to realize that there are actually two different distinct phases of motion for mass M1. In the first phase of motion, it is accelerating over the path of delta x1. And that means that it's governed by a completely different set of motion equations. For delta x2, though, it's moving at a constant speed. Now, the speed at which it moves is exactly equal to the speed that it last had at the end of delta x1, what we would call our final velocity from that part. And when it stops accelerating, that means that its initial velocity for delta x2 is going to be the same value. And in fact, it will remain that same value as it moves down the end of the track. Now, keep in mind what we're attempting to do here, and that is to determine the total time of motion for cart M1. And so in order for us to do that, we need to take a look at ways to determine the time for each particular section of its movement, whether it be the accelerated motion or the constant speed motion. For the accelerated motion, we know that acceleration is equal to the change in velocity divided by some period of time, which we will call time 1. For the constant speed motion, it's actually a little simpler, and it says that the speed at which the object moves, which will be a constant speed, is equal to the distance that it travels, in this case delta x2, divided by the time that it takes to travel that distance, which we'll call time t2. So it should be obvious from these two equations that we can use time 1 plus time 2 to determine the total time that it takes for the cart to move down the track. Now, we said that this experiment was an application of Newton's second law, and here's where that comes in. We need to know this value for the acceleration in order for us to be able to determine the time for this first phase. And so we're going to have to utilize Newton's second law and the forces that are acting on M1 and M2 to derive an expression for the net acceleration of mass 1 and mass 2 as a whole. Because let's be clear here, as a result of mass 1 being connected to mass 2, they will both accelerate at the same rate. But finding this acceleration is going to be key for us to determine the time for this first part of its motion. And we'll also be able to determine the final velocity, or the change in velocity, which will give us the final velocity for the first part of motion. And knowing that final velocity will tell us how fast it's moving in the second part. And then once we know the speed at which it's moving and we measure the distance over which it moved, then we can solve for the time it takes for the second part of the path. But now we'll need to take a look at the forces that are acting on M1 and M2 in order to determine the acceleration of the system. So in the moment immediately following the loss of friction acting on M1 as a result of the air flowing through the air track, we can analyze the forces acting on M1 as follows. We said before that there is a force due to gravity which acts in the downward direction. There is the normal or supporting force that acts against the force due to gravity. And there is also the tension force T acting to pull it down the length of the track. We'll next set up a system of equations to analyze the forces that are acting on M1. In the vertical direction, the sum of the forces, ends up being equal to the normal force acting upward minus the force due to gravity acting in the downward direction. And these two forces end up canceling each other out as a result of them having equal magnitudes but acting in opposite directions. In the horizontal direction, however, there's really only one force that's acting on it. That is the force due to tension. And if we represent the force due to tension in terms of mass and acceleration, we end up getting something that looks like mass 1 times the acceleration of mass 1. And I'm not going to differentiate the acceleration here because mass 1 and mass 2 are connected, and as a result, they will share the same magnitude of acceleration. Now, for mass 2, things are a bit different. First of all, we should realize immediately that the forces acting in the vertical direction, really, there's only two of them. And in this case, it's the tension acting in the upward direction and the weight of mass 2 acting in the downward direction. You should notice that when I am referring to my forces as being either positive or negative, I'm using the convention set up here by my axis system. And as long as I stay consistent with that, with those axis labels, then we shouldn't have any problem with the calculation. Now, horizontally, we should realize that for mass M2, there are no forces. So really, I should have probably started out by saying that the force in the horizontal direction is 0 because there are no forces that are acting in the horizontal direction. However, if we take a look at our expression for the forces in the vertical direction for mass 2, we realize that we can actually simplify this in terms of, again, the mass of the object, mass 2, and its acceleration. Now, because this is actually accelerating, I'm going to refer to the acceleration for mass 2 as negative, because again, I'm using the conventions set up by my axis system. And so as a result, it's going to be the same magnitude of acceleration as I had for my expressions relating the forces in the horizontal direction for mass 1. And this is because, once again, these two masses are connected and they're part of the same system, and so they will accelerate at the same rate. Now, at this point, I want to take the expression for the forces in the vertical direction and flesh them out just a little bit. So I'm going to rewrite them as the tension acting upward minus the weight of mass 2, which I can replace with m2 times the acceleration due to gravity, and I can set that equal to, again, what I had before, mass 2 times the acceleration of the system. Now, knowing that from the equations for mass m1, the tension in this system is actually equal to mass 1 times the acceleration, I can replace tension for mass 2 with that same expression. And so now I get something that simplifies like this. Mass 1 times the acceleration of the system minus mass 2 times the acceleration due to gravity, that's this expression, which is the weight of mass 2, is equal to mass 2 times the net acceleration of the system. And what I'm going to do is I'm going to pull that negative term out here. And so I end up getting something that looks like this. Now this is important because I have an expression involving quantities that I know, for example, the mass of the first object and the mass of the second object and the acceleration due to gravity and the mass of the second object. And now I can solve for the acceleration by taking all those terms and getting them alone so that acceleration can be solved for. Using the previous expression, we can apply a little algebra and rearrange that expression to get it in the form that it looks like here. And again, it involves values that we either know or that we can readily measure. In either case, we'll have a value for the net acceleration of the system. Now remember, the acceleration of an object is also equal to its change in velocity that it experiences over some period of time. And if ultimately we're trying to determine the time it takes for mass m1 to go down the track, well then finding the time it takes for that first section is going to be important in order for us to determine the total time. But the problem here is that we now have two unknowns. Okay, so we were able to solve for the net acceleration of the system, but we don't know the change in velocity, and again, we're looking to find the time for that first phase. Well, what we can do is we can use our value for the acceleration, and we can solve for the change in velocity using another kinematic equation, namely this one, where we're talking about the initial velocity of this cart being 0, so that part of the expression goes away. And again, we're only talking about the distance covered for delta x1, which will help us find the final velocity for that first part. Now, once we have our final velocity, realizing that the cart started from rest, this is equal in magnitude to the change in velocity. So now we can say that we do know the change in velocity for the first part. And having the acceleration and the change in velocity known, we can rearrange this expression and solve for the time it takes for the first portion of the cart's motion. Now, as we get into the constant speed portion of the cart's motion, most of the difficult math has really already been taken care of. We will have been able to find the final velocity of the cart after the acceleration portion, which is equal to the velocity of the cart for the second portion. And with that value, we can measure the distance that it travels for the second portion. And as a result, we can determine the time that it takes for the cart to travel for that second portion. So with the value for times T1 and T2 in hand, you're now in the position to accomplish the objective of the experiment, and that is to determine the total time it takes the cart to start and end its motion, both for the accelerated portion and for the constant speed portion. Again, recall that we are going to use the acceleration of the object in the first part of its motion to determine that time. And for the second part, it'll be moving at a constant speed. And as a result, we'll be able to use that fact to know the velocity and the distance over which it traveled to solve for time t2. Now, the expression you get for the total time is going to look, well, it's going to look a lot more difficult than I've showed it here. And what you need to do is keep that in mind, that so that when you get an expression that looks something like this, don't get scared, don't run away. Just realize that this is the expression for time from part 1, and that this is the expression for time from the second part. Just keep your wits about you, and as you go through and calculate, be aware of signs and your order of operations, and in the end, you should be able to determine a theoretical value for the total time of travel for the cart. As with any experiment, the determination for whether or not your experiment was successful usually lies in your ability to get the experimental value for the quantity you're trying to measure to agree with the theoretical value within some range of uncertainty. And so, as you can imagine, we're going to have some uncertainty involved with this because we're going to be making measurements specifically for mass m1, mass m2, the distance that the cart travels, delta x1, which will be equal to the height of mass 2 above the ground, and then the second portion, the constant speed portion of travel, delta x2. So along with your theoretical value for the total time, you should be able to determine the uncertainty involved with that theoretical value. In the end, you're going to carry out the experiment, and you're going to do 10 trials, and over those trials, you'll have a value for the total time that is going to vary. And so with that random uncertainty, you should be able to determine the standard deviation of those values, and in the end, you'll be able to get a range for your theoretical value, and hopefully your experimental value will overlap that, and in the end, you will be able to hopefully say that you completed the experiment successfully.